Today, I'd like to take you through some elements of my own journey in deep learning. I hope that can be useful for this crowd. Don't hesitate to ask questions along the way, and we have plenty of time at the end. So let me start sort of going a little bit chronologically. How did I get into machine learning in the first place? It's really at the time when I was finishing my undergrad and shopping for potential research directions and supervisors. I read a lot of papers. I wasn't sure what I would do, and you know, maybe by chance I started reading neural net papers. These are some of the very few and early neural net papers. In particular, the work by Jeff Hinton and David Rumelhart and the other group of people, a lot of them coming from cognitive science, calling themselves connectionists. If you're interested, there's a lot of interesting things about that group and how it has influenced the early days of deep learning. And so I decided to get into neural nets. I really fell in love into this direction, and I'll explain why. But my master's then, starting in '86, was about Boston machines, which were just a new thing invented by Jeff Hinton and collaborators. And I played with it. I made it learn to classify phonemes. And then I got to know about the backprop that came out slightly after Boston machine. I got excited, started working with that, and that was the heart of what I did during my PhD thesis starting in '88. One of the important things there is that in '88, I went to the Connectionist Summer School, where there were probably a couple of hundred grad students. I met with many other people sharing my passion. And that really meant something important in terms of motivation, being part of this, at this time, very, very small community. But of course, as you know, that grew over the later decades. And then for the next 3 years, I worked on various kinds of artificial neural nets, recurrent nets, conv nets, again, applied to sequences and speech, and combining them with probabilistic models. In particular, at the day, hidden Markov models were used for speech recognition. So I worked on how to bring these two things together. So I guess the main message here is follow your heart and go for something that appeals to you. That really is the, the main thing. So what is it that appeals to me around 85, 86, and then continuing for decades still to today, was this, at the time, not mainstream idea, not mainstream hypothesis that there may be a few simple principles that could explain and give rise to intelligence. And of course, if we understand those principles, then you know, they can help us both understand our own intelligence, animal intelligence, and build intelligent machines. So this is a little bit by analogy to thinking about physics, where really there are just a few laws of physics. Of course, their combination and their composition and the complexity of the dynamics in the real world give rise, and in brains may give rise to very, very complicated systems. Now, how could that be possible that just a few principles are sufficient? And of course, if you think a little bit about it, you need to have learning, because in those days, the dominant AI approaches were not using learning. They were classical symbolic AI, where knowledge had to be provided by humans. And so an AI needed a lot of effort from humans to craft all of those pieces of knowledge and put them together in a coherent way, which turns out to be impossible in most cases of interest. And instead, if we have a few general principles, what these principles are, they don't contain the knowledge as such. They contain the recipes for acquiring that knowledge. And that's basically what machine learning is about, of course. So, so the contrast is most of the knowledge in machine learning is going to be provided from data, whereas when I started, it was all about knowledge engineering. And the algorithms of the day, they were taking those pieces of knowledge and doing inference. In other words, combining those pieces of knowledge to come up with answers to questions, but often requiring very expensive computation to really get strong answers in large systems. And I'll come back to that. And also these systems were lacking notions of uncertainty and probability that are at the very heart of what we're doing in machine learning. They were working at the level of these abstract symbols, which is quite interesting, but they were not grounded in low-level perception and action. So really the early work in neural nets and machine learning was about dealing with these issues. But as I'll come back to at the end, we are still kind of missing some of the things that the classical AI was trying to do in terms of higher level cognition. Okay, so let's try to think a little bit about what machine learning is trying to achieve. And this is something that in my kind of first 15 years of research has been really at the center stage of my thinking and has inspired me. And it was a little initially like kind of a mystery, like why are these big networks, I mean, big for the day, they were like tiny compared to today. How are they able to generalize? What even is generalization? So if you think about just say observing configurations of values of variables, like in the figure you have 1, 2, or 3 variables that have been discretized in 10 values each. So if you only have one variable, then you can just count how many times each of the values come, and you basically have all the answers to any question you can ask. And in principle, you could do the same thing with more variables, but now the number of configurations of values just grows exponentially with the number of variables. And that's the curse of dimensionality for machine learning, at least, that we never have enough data to be able to like directly tell us what's the probability of a particular configuration. And of course, if you can answer the question about probability, you can answer questions about, well, if this variable takes these variables take these values, what should be the values of other variables? So it's really at the heart of what we're trying to do in machine learning. So this looked like a puzzle, and for many years I've been wondering, like, how did neural nets manage to solve this? I'm going to try to explain the insight I got in the mid to late 90s that was at the heart of, then became at the heart of a lot of the work I did, for example, with word embeddings and convnets and other important high-dimensional spaces in which we use machine learning successfully these days. So the dominant methods in machine learning in the period from the early 90s to the end of the 2000s, now it's like 2010, were what I called local machine learning methods. And think of classical methods like nearest neighbor methods or kernel machines. For the most part, what they do is they partition the input space into regions, and then it's like the configurations I was talking about in my previous slide. For each of these regions, we're going to learn what the answer should be based on the data that falls into that region. So it's better than the histograms I showed before, because you learn where the regions are based on where the data is. But still, there's a problem, which is that if you want to have a fairly fine-grained description of the function you want to learn or the distribution, you would like to have an exponential number of regions, in particular to be able to say things about places you've never been before. But you can't. You need data in each of those regions. So how do neural nets solve this problem? Well, let's consider a very simple one hidden layer MLP with 3 hidden units. So each hidden unit is just like, roughly speaking, a linear classifier with a bit that says you are on one side of the line or the other side. So these are the 3 colored lines here. And now if you look at all the intersections of these lines, you see that the number of regions that they determine can be exponentially large. in the number of neurons and the dimension, input dimension. I mean, both have to be large. And that's kind of interesting because we don't need to have data for each of those regions, because the learning essentially focuses on learning where each of these lines should be, and it only needs data from each side of each line, right? So there's something like really funny going on here, where you can learn about an exponential number of things, but with a sort of linear amount of data. And I think that's the example of power of compositionality that even the most basic neural nets boasts. Here, what's happening is we can compose the features that are learned. Each neuron in a layer is like a particular feature, and we can learn about each of these neurons, but then we can say something meaningful about any new composition of values of these features. All right, so the road to deep learning really that became more obvious in the beginning of that century is that in order to make it successful, we need, for deep learning, at least as you know, lots of data, very flexible models, like, you know, enough layers, enough units to represent very flexible functions. That's really a key ingredient that we see today realized in large language models, for example. And of course, because we have these large models, we need enough computing power, and that was a problem in the 90s. And really, it's the advent of GPUs, as you probably know, that made it possible for neural nets to suddenly become relevant. The fourth point maybe is less obvious, but in general probabilistic machine learning, even if you have knowledge, answering new questions might be intractable. But with neural nets, somehow we are able to make computationally efficient inference by training the system to answer the questions we are interested in. And then there's this thing about this compositional structure I've been talking about, which more generally you can think of inductive biases or assumptions that can defeat the curse of dimensionality and achieve strong generalization to new cases. Okay, so that's what really I learned in the first 15 years of my journey. But you know, everything in this slide could be said for any machine learning method. But neural nets have this really interesting and exciting origin that has motivated me from the beginning that I mentioned, is that they're inspired by the brain. Somehow studying them may tell us something about how the brain works, although many neuroscientists would, at least in those days, claim, of course not, the brain is much more complicated. I think there's now a large crowd in computational neuroscience that takes deep learning seriously because it's working so well. And it's interesting that the synergy between the two sides of the equation, from neuroscience on one hand, or brain sciences on one hand, and AI on the other hand, is something that has really allowed deep nets to be what they are, but also can go in the other direction. And I see more and more of that, and I've worked on these things as well. So in neural nets, we have a large number of simple adaptive computational units, and they form patterns of activity, which we call representations, or more precisely distributed representations, because an entity like a symbol is going to be represented by this rich pattern of activity. And that's basically what is behind the idea of word representations that I introduced in the NeurIPS paper in 2000, and that is still at the heart of current natural language processing based on deep learning. Another thing that's been really kind of the core recipe of deep learning that we focused on starting near in the 90s, but then also in the teens of this century, is that we see this expressive power arising from the combination of three things: an objective function or reward function, something we'd like to optimize, some mechanism to change the parameters, a learning rule, an optimizer, and we like stochastic gradient descent variations for many reasons, and a family of functions, or in neural net parlance, an architecture, which is just a way to parameterize a family of functions. So it's a very simple thing, but you have, and now we sort of take it for granted because everything you read in deep learning has that structure, but in the 90s, it wasn't like this. There were lots of other kinds of neural net approaches that didn't fit this mold. And going forward in the future, I think we should allow ourselves to explore other ways of thinking about this. So this is really what people call the end-to-end learning methodology, which is incredibly powerful because all the pieces of the puzzle adapt to help each other. Okay, so to recap, in machine learning, with this, especially this end-to-end approach, we have a family of functions, we have tunable parameters, we have examples sampled from some unknown distribution. We have a way to measure how well our trained function is doing, and then we have an algorithm to change the parameters of our function so as to approximately minimize that error. And that is almost always iteratively because we don't have analytic solutions for complicated things. All right, now I'm going to do a little parenthesis about recurrent nets to tell about a lesson, I think, that goes beyond this particular work I did in the 90s. This work was essentially a negative result about recurrent nets. It's called Learning Long-Term Dependencies with Gradient Descent is Difficult. It was saying that there is something inherent about these dynamical systems. In fact, more than recurrent nets, almost any parameterized dynamical system trained with gradient optimization, which was the basic recipe, as I said, that makes it really hard to learn about long-term dependencies. And in fact, this obstacle has been at the heart of a lot of work trying to bypass it, but it's only around 2014 with our work on self-attention and the related work that was going on neural nets with memory that I think we collectively unlocked this apparent, the very, very big challenge of training systems that can capture long-term dependencies. I'll come back to attention. But really what is going on in dynamical systems like recurrent nets that we're trying to train to achieve something is that it's called the gradient vanishing and gradient explosion problem. But let me explain what happens if you have notions of dynamics. You have the state of the recurrent net that's going to be evolving through time. And if you imagine you just want to use your recurrent net to store one bit of information, then a natural way of doing this is to have those dynamics have two basins of attraction. So either depending on where you start, the dynamics would go to one region, which represents, say, a bit equals 1, or the other region where it represents bit equals 0. So this is something we can easily code in a neural net. But the problem is about learning, where these, how to set up those dynamics. Once you have it, it does store information very reliably. And the problem is that with these attractors, you get information loss. In other words, all the trajectories that are in some basin of attraction converge to the same attractor, which may be a single point, a fixed point, but it doesn't have to be. And so what that means is once you get to that fixed point, you don't know where you started from, which means the derivative of the final state with respect to the initial state is infinite. If you start on, well, it's either 0 or infinite. So if you start from inside the basin, it's 0 because any small change would still get you to the same place. And if you are near the boundary, then it's infinite because a small change makes you go from one place to a completely different place. So that's really the reason why we have either vanishing gradient or exploding gradients. I'll skip the math details. So now let's go back to this notion of learning representations. Really, that's the distinguishing feature of neural nets. There's still a lot of other machine learning methods that lack this notion of representation. And that's why we, with Jan McCann, we created this conference called iClear, International Conference on Linear Representations, because we thought this was really the central property. It was not so much that it's neural, it's about learning representations. And that, yields all kinds of questions, like what kind of representations do we want? What is a good representation? And the general idea we put down is that, well, a good representation is one that makes some tasks easier. So it's not a very precise thing, but of course, when we train a supervised net, the intermediate representations are useful to making the predictions at the output. But the same idea works for unsupervised learning or self-supervised learning. One of the first really important application of these ideas in my journey was the work that I mentioned on learning word embeddings on neural language models. So we had a paper at NeurIPS 2000 and then a journal paper 3 years later. And what was the idea? The idea was to not just operate on symbols and counts, which was the sort of state-of-the-art way of doing things, what's called n-grams, but associate to each symbol a vector, a set of real numbers that would be free and that we would learn. And the key insight here is that although we may be interested in these relative counts, for example, of probability of some word given some other words before, if we learn a separate parameter for those probabilities for each of these configurations of words, we would be having a hard time generalizing to new configurations. That's the curse of dimensionality thing I was talking about before. But if we associate each word with this word embedding vector, then the same parameters which describe the meaning of a word or it's how to use it would be used in all of the configurations that include that word. So we can implement that idea with a neural net whose first layer maps the symbols to their embeddings, and then it's like normal calculations. So that was the idea. And as you probably know, this idea worked incredibly well. But the notion of compositionality in deep learning is actually, also has other aspects. For example, there's a notion of hierarchy of composition. So, the idea with the word embeddings is it's like the features I was talking about. We can compose those words together in new ways. But there's also this notion of hierarchy of features, which really is behind the idea of deep learning, that we're going to have many transformations, and each level is a kind of nonlinear but fairly simple transformation of the previous level. And we know that humans organize knowledge in this hierarchical way, whether it's speaking about images or text or speech or any almost everything. And that has been a big inspiration for the work we did in the 2000s on neural nets that were deeper. And by the end of the knots, these deep nets were starting to show some really exciting impact in applications like speech recognition and then computer vision. This shows what happened when people started using these deep nets in speech recognition around 2009. And then this was actually put in Android phones very quickly. And they were, these deep learning speech recognition systems were available in 2012. And then computer vision, really got its revolution after the ImageNet breakthrough in 2012, with the error rate decreasing very, very rapidly. And there's something interesting. So going from pre-deep learning to post-deep learning, it was a big jump, but then it continued going down as people engineered these architectures and found better ways of training those large neural nets. Okay, so this period, from a personal journey point of view, of the late 90s and first decade, more or less, of this century were actually not so easy because most people turned their back or on neural nets, and it was really, it took a little bit of stubbornness to persist through this neural net winter. I had the impression that at that time that a lot of the AI research, and including machine learning research, kind of lost its ambition to reach human level intelligence. And this notion of compositionality and distributed representation, compositionality with features, compositionality with depth, I really thought that this was a key to learn really complicated things and generalize well. That was needed to approach human level intelligence. And now I think it's part of the answer, but we need other things. So in those days, people were focusing on much simpler approaches to machine learning, simpler in the sense that, it was easier mathematically to analyze what was going on. And even today, there's a lot of interesting theory work on neural nets, but there's still a lot of things we don't understand. From a personal standpoint, what I found hard was because the trend of the day was basically moving away from neural nets, it was difficult to convince my own students to work on those topics. But I persisted. And one thing that is important about being stubborn is you also need to balance that with good rationality. So intuitions are amazing. I was following my intuition, but you need to validate them experimentally or mathematically to prove to yourself and eventually to others that there is something important there that's worth continuing to explore. And so there's this image that I like, that when you have intuitions, you're pulling on threads to clarify them, because the initial intuitions are a bit vague. You need to work a little bit to kind of think more and again more, and ask questions, lots of questions to try to understand, the why questions. Why is this happening? What is going on? What may be the key principles? The other thing that really helped to go through that period was a kind of support group. So the Canadian Institute for Advanced Research called CIFAR created a research program that still lasts to this day, focused on deep learning. And there were just a few people really still kind of believing this was important, but having them and meeting them regularly really meant a lot in terms of motivation. So we don't do research by ourselves, really. We do it in a group, and we seek the sort of the feedback of others. We want others to appreciate what we're doing. And if we don't have other people who kind of care about what we're doing, then the motivation is not as strong. So this is also quite an important lesson. All right, so post 2012, an important thing that happened in my group is the work on unsupervised generative models. So actually, we had been working on this for at least 5 years with different methods, in particular denoising autoencoders that which have ingredients that are still used in today's large language models. But the big breakthrough in terms of publications and at least for a number of years impact was the work on GANs, the generative adversarial networks. And you probably know that they have really opened the door to neural nets that can generate very complicated distributions, like all of these images, of course, that are all like fake, and you can see the progress of the method. And what's interesting here, again, going back to the sort of personal journey aspect, is in 2014, when we run our experiments, we didn't think that it worked that great. So the math was cool, but the results were, not particularly kind of convincing, and it was hard to make comparisons because we couldn't compute likelihoods. And really, it's thanks to other groups that picked up this work and improved the architectures and trained for longer on higher resolution images that eventually it became what it was. So it's again an example of science is, many people building on each other's work to end up with what we get. And now, okay, the other sort of really important transformation that happened around those years in my group is the work on attention. And if you know a little bit about modern deep learning, you'll know that attention is at the heart of it and incredibly powerful. And I think we still have a lot to get from these ideas. It's part of things I'm doing these days. So this came because we were trying to apply recurrent nets to machine translation. And in machine translation, to predict the next word, say in French, given some text in English, it really helps to focus on just one or a few words in the English source text that are kind of the word-to-word translation or the most relevant to make the prediction. And adding an explicit architecture for doing this completely changed the performance of the networks we were training. And then became quickly the norm and was adopted by Google and Google Translate. And just a few years later, like almost every machine translation used this, but then almost every other natural language processing systems, large scale ones, ended up using this, in particular thanks to the work on transformers, which added the idea of stacking these attention layers on top of each other. Now I want to come back to the thing I was talking about regarding recurrent nets. So what is happening with attention mechanism is that we don't rely only on the state of a recurrent net. In fact, we can get rid of the recurrence altogether. That was the transformer attention is all you need insight, because the long-term dependencies can be captured by attention. So the output at some position t can be obtained by attending something that's very, very far in the past. So, how is that even possible? Well, one way to think about it is to think about it in terms of memory, that it's like if the network doesn't need to compress all the past sequence into a, sort of small vector. Instead, it has access to the whole input and it can, fetch in there what it needs. So really, attention is bypassing the issue of learning long-term dependencies in RNNs. That was the beginning of an important milestone in my early career. And you can read more about this in a paper in NeurIPS 2018 on what's called sparse attentive backtracking with Rosemary K. Then, of course, this came out in 2014 on Archive, 2015 at iClear, and then just 1 year later, AlphaGo came out, and deep learning became incredibly important as part of reinforcement learning. And DeepMind then later used attention mechanism to achieve an amazing scientific breakthrough of protein structure from sequence, mapping the sequence of hundreds of letters describing a protein to its 3D structure. That I think is going to be the start of a complete revolution for biology in the coming years, by the way. So again, using both attention, but also graph neural nets, which arose shortly after the attention papers, and to which we also contributed with the attention graph neural nets. Okay, so 2019, Jeff Hinton, Jan LeCun, and I got the Turing Award, and I had started getting prizes even before that, but then it accelerated after this. So all these prizes and awards, all these recognitions, they're dangerous. They can just make your ego too large, and that's not good for science. It's better not to think about these, not to aim for them, not to aim for recognition. These can be really dangerous distractions. The problem is ego can blind us, make us overconfident, and it really doesn't help us to make important scientific discoveries, because it hurts our ability to be flexible, to change our mind, to question what we took for granted, to also listen to others who disagree with us, because science is about being rational. And if there is something wrong that we don't see because we have blind spots, we need others to point it out to us. In my career, I actually changed my mind several times about important kind of philosophical ways of thinking about machine learning. For example, in the 90s, with Jan and I were really focused, in the belief that the only thing that could really work with, at least with neural nets, was supervised learning. That unsupervised, was hopeless. But in around 2005, thanks to Jeff Hinton, we started working a lot on unsupervised learning, and we became convinced that this was key to intelligence. Of course, humans learn a lot about the world without a lot of labels. And I've changed my mind many times before. So for example, recently I've been thinking a lot about Bayesian machine learning, something that I thought didn't make much practical sense until recently. And another kind of anecdote like this is, although my group introduced this soft self-attention, I now think that this soft attention is not sufficient, that we need stochastic hard attention. And actually we had a paper early on showing that surprisingly it works quite well, even though you break the end-to-end learning story. But there are good reasons that I may probably not have time to talk about today. So the rest of my presentation actually is moving closer to what I'm doing now, but starting with this notion of representation learning that I discussed a lot. Already in the mid 2000s, I said we were asking ourselves, so what would be a good representation? And so that's one question. But then if you're doing unsupervised learning, which was exactly what we were doing, there's the question of what should be the kind of highest level of representation. And to me, it was obvious that the highest level of representation should be the highest level of abstraction, things like words, things that we reason consciously over, things that are the causal factors that explain the data we're observing, explanatory variables, and understanding how these high-level variables are related to each other, I thought was really what we should be focusing on. And I still think that, and I still work on that. So we wrote about this question of, well, how do you discover disentangled representations in particular in the paper in 2013, because the trouble is, if you don't have supervised learning, it tells you what each of the units should be doing. There are many ways that you could represent the same information. And we have this intuition that some ways of doing it are better. For example, maybe if there are sparse representations, meaning that for any particular input, only a few concepts are relevant. And also that the dependency between those concepts is sparse. This is something I started really working on in 2017 and I still work on. And that unlike a lot of the work in disentangling, these high-level factors, variables, they're not independent. You construct sentences that relate words together. There are causal dependencies between the high-level variables, and we need to also learn the joint distribution at the high level. So I talked quite a bit about compositionality in my presentation already, but in the last 5 years, I've been kind of really thinking, well, we've exploited some particular kinds of compositionality. Like, I mentioned how different features could be combined in one layer. So that's the distributed representation compositionality. We also exploited compositionality of functions of functions where you have a deep net, where each layer is a function of the previous one. And that's a different kind of compositionality that's interesting, that actually may give us an exponential advantage. Both of these may give us potentially an exponential gain in terms of representational power. But there's another kind of compositionality which we use in language, where we combine words, and we can even have recursive compositions to give meaning to complex ideas. And this is not something that current deep learning really does, even in language models. But in any case, there's this other idea that is coming up. Once you start doing a bit of theory behind those compositionality ideas, that, well, not every function you'd like to learn or every distribution you'd like to learn may have an efficient compositional representation. But humans seem to exploit that kind of inductive bias. In other words, there is compositionality that seems to be useful to describe the world as we imagine it, as we model it in our brain. And it may help to capture not every possible function, but the kinds of distributions and functions that we see around us, or at least that we're good at understanding. So the other thing about these high-level abstract representations that I got into in the last few years is learning how they're related to each other. So I mentioned that, and I'll explain why the causal aspect is interesting. Like, is one variable causing another? That's a very basic question that humans seem to be focusing on. And when you start reading about causality, one thing that really should strike you is there's the focus on the notion of intervention. What's called an intervention is an action by an agent at an abstract level. And an intervention changes things, but in a very special, sparse way. We change one thing, we open the door, and then suddenly the whole house gets to be cold. There could be consequences, but it starts from an action by an agent, which we can often describe in a single sentence. So how do we discover these sparse dependencies, causal dependencies at the high level? This has been at the heart of many of the questions I've been working on, especially in the last couple of years. And it's important to help us deal with what I think is a major limitation of current machine learning, which is a more powerful form of generalization that humans seem to benefit from, which we call out of distribution generalization. In other words, if we want to train from some data, but then we want to be able to generalize from data that comes from a different distribution. Well, how could that even make sense? Our theory doesn't tell us about that because, well, it could be anything, right? But humans seem to be good at that. And clearly humans seem to be good at that by reusing the knowledge they have, the pieces of knowledge they have, in applying them in new ways to face new settings. So maybe our current neural nets do not modularize knowledge in a way that lends itself as well to this reuse of pieces of knowledge that are just needed for a completely new setting with a different distribution. Yeah, so I think this is the same thing. But also saying that in industry, this is like in applications of machine learning, this is a big problem, because we typically are going to train a system on some collected data, which maybe comes from a particular time, a particular country, and then we'd like to have a system that works everywhere and continues to work when things change in the world. And if you look at language, linguists have been thinking about this notion of generalization to new configurations of word, to give meaning to new configurations you've never seen, call it systematicity. There's a systematic way in which we can generalize to combine, for example, here, visual concepts of vehicles to make sense of this new vehicle that you see on the right. And in the last few years, people have been kind of evaluating how neural nets would do if you train them on some configurations of concepts, and then you test them on new configurations that have zero probability under the training distribution, and they don't do well. They don't have this kind of systematic generalization that we would like to have. So this is something we need to better understand for practical reasons, but maybe also something fundamental. And the theory that I'm working on is that there's probably an explanation to explain why humans are good at it and current machine learning is not, to explain this gap. So it's a gap in like sample complexity, the number of examples needed to learn a task. Of course, how well you do on a new task, on a new distribution, out of distribution generalization, but also you might not do very well initially. So humans just need very few examples to adapt. People have been studying this K-shot generalization, for example. So the speed of adaptation is something that matters. And then other things that we have not been very good at incorporating in machine learning, like the ability to discover causal structure and reason with those cause and effect relationships in a way that exploits a kind of compositional representation. So the hypothesis I have is that this gap emerges from something that humans benefit from, and maybe to some extent other animals, but that is missing in current machine learning. And it's something that we can associate with conscious processing in humans. So let me explain why I think so. When a human is faced with a novel or rare setting, for example, driving in Australia or in London after having spent your life driving in North America, well, there's one little rule that changes. You now have to drive on the left rather than on the right. Everything else is more or less the same. And humans can adapt pretty quickly to this, but they don't adapt. They adapt in a special way. So if you're like, you rented this car and now you're in this place where everybody's driving on the left, you need to attend. You need to be consciously attending to what is going on. You can't just go and drive by your habits or you're going to make an accident. So when we are faced with these novel out of distribution settings, we don't follow our routine. We use conscious thinking with attention, planning and reasoning in order to face these changes. So that's what I mean. It seems to be that, in fact, if we look into the brain, when this is happening, we see that the forms of activity in the brain is different. And this is connected to another observations from cognitive science, that there seem to be different kinds of tasks that can be labeled system 1 and system 2. The things that we do with our routine and intuitively without having to think about it, unconscious computation is in more or less the system 1 category, and that's where current deep learning is really good at. But there's also this what you do when you're facing these new situations. So you consciously attend and you think about things, and it's very slow and painful in some way, but there's and it's sequential. It's like one little piece of reasoning at a time. We can verbalize what we're doing, why we're doing it, at least at that level of representation. So knowledge is more explicit, and this is something that exploits this compositional structures that I said are missing, but would like to bring in deep learning. So yeah, how is this related to notions of agency and causality? I'm going to try to give you a glimpse of that, and how to, what we would like is to build deep learning systems that have both of these things. And by the way, this in a way is also a kind of break with the sort of beliefs that maybe some of my colleagues have, that we need to do everything with the current deep learning recipe, like end-to-end learning. When you start thinking about system 2 with, you have these symbols that you're going to be manipulate and reason over, it's less clear that the same recipe is sufficient. So in particular, you want a kind of modular representation of knowledge, that knowledge be factorized into recomposable pieces. And this is not something that is obvious in current deep nets, where you have this one big homogeneous architecture. Of course, on the output side, like if you output words, or on the input side, you may have symbols. But the pieces of knowledge themselves, everything is mixed together so that when you face a new distribution, every weight needs to be updated, and that means transfer learning is very slow and inefficient. Okay, so here's a way to think about how maybe humans and maybe coming machine learning methods can deal with out of distribution generalization. We're going to need to make some assumptions because okay, so we're going to get rid of the ID assumption, but we need some other assumption that allows to transfer knowledge from one distribution to another. And one way to think about it, coming from the sort of physics angle, is that there are shared laws of physics, but in different places at different times, because of different initial conditions, different interventions, you get to observe very different distributions. So for example, if you're on the moon and you watch around you, it looks very different from if you're on Earth typically. So the distributions almost don't overlap. And that's interesting because it's the same laws of physics, right? So if we have a good model of what is going on here, like gravity and the presence of an atmosphere and so on, we can quickly generalize from understanding data from one kind of distribution to another kind of distribution. Because if we are able to learn these shared parameters that are about the causal dynamics, then we only need, when we go to a new distribution, to make guesses about what were the initial conditions, or what's different. It's just a few variables really that really may have a drastic impact, like the constant of gravity and the lack of atmosphere. So causality is really a framework that has a solid theoretical grounding to think about out of distribution generalization. So the idea is that a causal model is not like one distribution. It's really a family of distributions that, or if you want, family of tasks that share the same parameters. What changes from one distribution to another is that you have these interventions or if you want, setting of some of the high-level variables that explain the difference. So what we've done is, instead of directly learning a distribution as one thing, we're separating what's stationary knowledge, things that are going to be the same overall distributions, that's like the causal mechanisms, like the laws of physics, from the things that may change, the things that are non-stationary. Maybe there are latent variables that you don't directly observe, but corresponding to these different abstract things like gravity constant and so on. So this is why I think causality is so interesting, but it's just one of many inductive biases that we can get inspiration from human intelligence. So humans seem to be thinking a lot about why, and attributing explanations for things they see, for changes they see in the world. So that's one thing, but there are other things like all of the work in neuroscience and cognitive science about working memory and this existence of a bottleneck. Your working memory can only hold a handful of items at a time. And it's weird because your brain is huge. It has almost 100 million neurons. Why would you have such a bottleneck? So there is a particular form of computation that seems to be going on in the brain where we focus on just a few elements at a time and only call upon the corresponding knowledge. So there's also a notion of modularity in the brain with potentially millions of experts in cortex, where when you think about some things, there's a dynamic selection of which modules are relevant at any time. And I have hypothesized that this working memory bottleneck also corresponds to an assumption that at least at the high level of these abstract variables, the dependencies are sparse because you can only do inference looking at a few at a time. All right, we've written a bunch of papers showing already that some of these inductive biases can bring better out of distribution generalization. The slides are going to be available, so you can look that up. And the last thing I want to mention is the work that we're currently doing that breaks a little bit with the end-to-end story with what we call generative flow networks, or GFlow nets. that you can actually apply to learn very complicated distributions like the Bayesian posterior over causal graphs, which is what we do in that paper. And the key idea is that we can use modern large deep nets to learn very complicated distributions that are needed for probabilistic inference and perform probabilistic reasoning that is learned on top of knowledge that may be actually pretty small, that can be actually learned from small amounts of data. So if you want to learn more, I've written a tutorial that you should be able to find online. In the tutorial, you'll see a dozen papers already on GFlow nets. And oh, last thing I forgot, very important for me, machine learning is having an impact on society. And that means we all have a new responsibility that did not exist 10 years ago. We, the scientists, the engineers, but also the entrepreneurs that are developing products, the governments, to make sure that AI is used, AI is a tool, but make sure that it's used in a way that maximizes its beneficial impact and minimize its misuse. And this is actually not a trivial thing, because the more a tool is powerful, the more it can help, but also the more it can be misused for the benefit of just a few. And for this reason, there are lots of concerns about using AI, in concentrating power in the hands of a few, in reinforcing social biases and discrimination. And something that scares me is also how it could be used to control people, to manipulate people. Think about AI driving political advertising, for example, or social media, which is already maybe happening. So these are, and then of course the military applications is something we should all be concerned about these days. But also we've been doing more and more work in our community and at Mila and my group in particular on applications of AI that are important and beneficial for society and healthcare, the environment, education, justice, all kinds of humanitarian applications. And it's important for us, our community, to work on these things because often there's a market failure. In other words, what is highly valuable from the point of view of society, like finding ways to capture carbon or other ways of fighting climate change or discovering new drugs to prevent the future pandemics, may not be so valuable from a commercial standpoint. And so the needed research and development is not necessarily happening. So governments should invest money in these applications, these beneficial applications of AI, and academics should invest their time to fill that gap between the societal and the commercial value of innovations, the gap that industry is leaving for us to deal with. Thank you. I'll stop here and be really happy to answer your questions.
Thank you, Yoshua, for the great talk. So we'll be taking questions in the room, but first question we have online from Tatiana Lichomanenko, and she says, thanks for the deep learning journey. Do you think that currently we formulate problems, tasks, and data sets which do not provide reasoning learning? The most tasks we solve is memorization or great impression of the distribution we see, but not reasoning or causality. And do you think we need some new data sets and benchmarks to be able to learn and understand causality? Thank you.
Yes. Well, first of all, I do think that there is reasoning going on in our large language models, but it's not exactly of the kind that humans do, although there are some relationships. So it's like we're just using the system one ability for reasoning, which is already interesting, but then it makes sometimes mistakes that if you had more like system two reasoning as well, you might detect as incoherent, for example, incoherent with the knowledge you have acquired. And then there's the causality aspect. There's more and more work trying to develop benchmarks because causal machine learning is in its infancy, and it's even hard to evaluate whether a system is working if you don't know the ground truth. So I think for a while, people will work on these synthetic systems. But one thing I'm really excited about is the applications of causal machine learning in experimental sciences, in particular in biology, because there we are in a setting where it's not a simulation. We can do causal interventions, which means like try things, change the activity, the presence of genes in cells, and kind of measure the outcomes. And thus, I think that we'll have ways of evaluating and proving that these methods are actually useful outside the lab. But of course, in the lab, in the machine learning lab, we need those simulations. We need those to quickly evaluate and compare different methods.
Has there been any consideration into focusing more on personality and creating machine learning in software that's kind of more targeted towards different styles rather than trying to make a one-size-fits-all model of cognition?
I don't know any work in that direction. It's already hard enough to do something that is able to kind of take intelligent decisions or answer questions intelligently. But I think it's an unavoidable kind of consequence of using machine learning that if you use it, even if you use the same data set, but even more if you use a different data set, what happens is if you train, for example, 10 neural nets on the same data, they will end up with different functions because of initial conditions and the randomness in training. And so they will kind of have different opinions on things. So it's already built in. Now, I'm not saying this is the same as the difference in personality that we have, but I think it's going in that direction. And by the way, it's important. It's important to have different, like, you know, people talk about diversity. It is actually important to have different, let's say, different theories of the world, different ways of thinking things, because not everyone is going to be right. And in human societies, this is extremely important. Like we need other people thinking differently than us, so that, you know, truth may gradually emerge from these incompatible viewpoints sometimes.
Thank you.
I think there was a question in the front, and yeah, so we'll take one here, and then we'll take one from Paris.
Thanks for your very inspiring talk. So you mentioned that you have changed your perspective a few times. I'm interested in particular in the from the frequencist to the Bayesian perspective. So I wonder if you could share a little bit more insight on your Bayesian perspective, since you also have the frequencist perspective. Thanks.
Okay, I'm going to do a 5-minute Bayesian conversion argument. Right. So first of all, if you look a little bit in the math and you want to do like really rational decision making, you know, like the Bayesian perspective imposes itself. But I'm going to give you a kind of toy thought experiment to explain why it's important. Let's say that you are in front of 2 doors. You can either go left or go right. And given the data that you have accumulated, there are 2 theories that compete to explain what's relevant here. Under one theory, going left, you might die, and going right, you would make a lot of money, or a lot of cake, whichever you prefer. And the other theory is kind of the other way around. If you go left, you get a lot of money and cake. And on the right, nothing bad happens. So maximum likelihood training, if you train like a single neural net in the usual ways, will randomly pick one of these 2 theories. So with 50% probability, you're going to end up with the wrong theory that says to go left, and then you're going to die. So you get what's called catastrophic errors with high confidence. In other words, the system is sure that you should do something, but it's wrong. Being Bayesian means entertaining all of the theories that are compatible with the data and then acting accordingly. So for example, in this simple case, you want to go right because, you know, maybe you get money, but maybe you get nothing, but it's the best option, clearly, in average, over all the theories. So that's one reason why you want to be Bayesian, because you can do safer exploration, for example. But also being Bayesian allows you to know where you might gain information. So where do the theories disagree? Well, in this case, they disagree on everything, but in general, you know, theories would typically agree on most things and disagree on just a few things. And those are the things you'd like to explore, right? This is where you want to go, where they disagree, if it's safe as well. So that mismatch between the different theories, which Bayesian modeling gives you, also drives curiosity and should drive our exploration as information-seeking agents. Okay, so that's the second reason why you want to do it. There's a third reason about reinforcement learning, model-based RL, but I won't have time to say it. But why are we not doing it? Why, you know, what I'm saying here should be obvious. I mean, people have been thinking about this for decades. So why is it that it's not yet in the state of the art in machine learning and deep learning? Because if you want to do the exact calculation that's needed to just think about enumerating all the theories that are compatible with the data, there might be an exponential number of them. And so you end up with intractable quantities that are needed to be computed in order to do this rational Bayesian decision making. Well, so recently I've realized that with the kind of large deep nets that we're currently able to train, we can actually solve this problem using what's called amortization. We can train a large neural net that can approximate sampling from the Bayesian posterior. And this is the last paper I mentioned is doing this sort of thing. And in addition, these posteriors don't have to rely on kind of excessive assumptions. So the way that Bayesian approaches have been handling this intractability in the past is making very strong parametric assumptions so that we can calculate these intractable sums or integrals exactly, or in a way that's easy numerically. For example, assuming that the posterior is unimodal, like you know, just care about one region in space. But neural nets can free us from this. That's what I realized in the last half year or so.
Okay, thank you very much. So maybe one more. So you mentioned your thought experiments. The two assumptions, is that something related to the prior in the Bayesian? Sort of prior knowledge.
I think the priors are not that important. I mean, like if you were parametric, yes, priors are important. But if you're like in the neural net world, with like these large neural nets, the priors are the things we already do, like you know, architectures and the SGD prior that you know wants things to be smooth and so on. So we already use priors. Like it's just that currently what we do is we just find one setting of the parameters that fits the data and is consistent with the prior. But what the Bayesian way is, you know, same prior, same, you know, likelihood, same data fit term, but we want to find all the settings of the parameters and we want to be able to integrate efficiently over them. And I think it's quite feasible.
Thanks. Okay, thank you. We have two questions in Paris about a slightly different topic. They're both related. So the first one is from Solal, who says, you said that AI has a big social impact. What is the best effort we can do as researchers to make the best out of it? And then the second question is from Iham. I do only one question. Oh, okay. Fine. So what is the best that we can do?
The best that we can do? Well, the good news is there are many things that we can do. So first of all, we need to read a bit about the potential dangers and misuse of AI. But then we can get involved. I think that's like an awareness thing. And if you're deploying systems, I think it's important to think about potential biases, for example, or understand that if you work for an organization that's going to build weapons, that's not a good idea. But then we can do positive things as well. Like we can work on these applications, and especially my bet is let's focus on applications where there's a huge social or environmental value, but very little work is going on, maybe because it's not profitable yet. Maybe the price of carbon is too low, right? Or the price of antibiotics is too small. And so companies don't do the work that we need now to solve big human, social, and environmental challenges.
Thank you. So the second question from IHAM is somewhat related. In the recent tech and model advancements, for example, GPT-3, we noticed that the research is linked to high computational power, huge data set, and a lot of money that could only be available in big tech companies. How do researchers look at this? This poses a struggle to smaller communities and researchers.
I can only say I agree. So how do we fix this? It's hard, right? So first of all, so some good news. There are lots of questions, like fundamental questions that we don't have answers to, that we can study in a smaller setting where we can take the current GPUs and maybe just one of them or 4 and not 2,000 and still like do really useful research. And a lot of the research going on in academia is like this. So we can't build these really large, train at least these really large language models or vision models, but we can still do a lot of interesting things. And of course, there's the theory aspect, but also designing new algorithms that, for example, incorporate the kind of inductive biases that humans exploit. These are very conceptual things. You can test them on reasonably scaled things. It doesn't have to be a trillion parameters. It could be, 50 million, and it's kind of easy to do on your GPU. Now, the other thing we can do is influence our governments so that maybe at an international level, or maybe large countries like the US can afford to invest in compute power for academic research in AI, and of course in other areas, at a scale that is needed to take some of the best ideas we have in academia and turn them into like really important high social impact applications. So we need governments to put money into the right thing, because they don't have enough money to do everything. But I think if they focus on the sort of large scale applications that matter to society and where industry is not going, because otherwise industry is going to do it. Why duplicate the effort? I think it's really worthwhile.
Are there any insight on how to make the gradual transition from what we learn in the slow causal system to the fast routine system, kind of like the driving in Australia that you mentioned?
Well, we can learn a lot about how it's done in human brains. So there's a lot that's been written in neuroscience and cognitive science about it. The theory that I find the most appealing is the global workspace theory, or its descendants called the neural workspace theory, that rely on this bottleneck I was talking about and the attention to select just some parts of the brain sort of compete with each other, first of all, because there are many configurations, many combinations of things that could happen. And just a few, think of like a sentence, a thought that you could express with words, gets selected through some process that we know about in neuroscience. It's called the conscious ignition process. And then that information gets broadcast to everything in the brain and drives your next decision. And you can verbalize what you were thinking about, but it also drives your actions and the next thoughts, right? So we know quite a bit about that architecture, if you want. And it needs, it's not like there is a system 1 neural net and a system 2 neural net. There's no such thing. It's all a neural net, but you have this attention competing thing that has a special structure that makes just a few symbols emerge and be combined in a compositional way to form the next piece of inference that we do at the conscious level, at least. And that then trains also your habitual thing. So, if you drive in this new place just a few hours, it will eventually very quickly become a habit, and you don't need to think so much about it anymore.
Okay, thank you. I have a question online from Zhonglin Li, who says, thanks a lot for the talk. For biological neural network, the way they're trained is through Hebbian learning, where weight updates can happen during inference. However, for deep networks, the weights are usually frozen during inference. Do you think such disconnections between training and inference could hinder the adaptability of deep models?
Okay, so first of all, we don't really know how synapses are updated in the brain. There's a Hebbian style that we can see, but it's probably more complicated. There are like theories in computational neuroscience which suggest that feedback connections, maybe going through the apical dendrites, may have a very important effect on the update. So it's not just Hebbian. There's other factors coming in which may implement something close to backprop. So there's quite a bit of research, people trying to build something that will have similar properties to backprop, but it remains local and biologically plausible. And we'll end up having a Hebbian style, but not exactly just the product of the pre and post. Regarding your question about inference versus training, I think this is a great question. Jeff Hinton has proposed many years ago the idea of fast weights. So the idea is to consider synaptic weights that have a short life. So in other words, they can change quickly and then they go back to some like base level quickly on the scale corresponding to working memory. So I think this is the best bet we have for working memory, and even short-term memory more broadly, like not just the current thought, but the thoughts I was having in recent minutes and hours. So the idea is to consider these fast weights to be part of the state of the brain, right? So normally we think of the state of the brain as just the activity of neurons, but you can also have these fast weights. That's 1,000 more degrees of freedom. So that's a lot that can store things for a short time. So in a way, they're part of the whole dynamics, and somehow we learn how to modify them. And Jeff had some like simple Hebbian learning sort of methodology that he experimented with his co-authors on these ideas. So yeah, I think this is certainly something worth exploring.
It was a nice talk, and I was wondering that your definition of conscious process discuss mainly about causality, but for my perspective, in my mind, I thought consciousness includes awareness of self. So any ideas that you have awareness of self in your conscious process?
Sure. So first of all, I'm sorry if you got the impression that I thought that conscious processing was focused on causality, because it's not. It's just one element. But there's a lot more, and I gave you a glimpse there in my presentation. But there is a paper, for example, that came out in the Real Society on inductive biases inspired for high-level cognition with Anirudh Goyal and me. That really goes deeper into this. As to what was the other part of the question? Sorry. Oh yeah, self. Yes. Sorry. I don't think there's been much work in machine learning on that front, but self is just a part of your world model. So we think of a world model as what's going on in the outside world, but it's also a model of who I am, where I am, what is my current emotional status, So there's a lot of evidence, of course, from neuroscience and cognitive science about that, and that we can reason about that. I think this, especially for tasks that involve multiple agents, where it's not just me, but also other agents that we want to represent in our world model. This becomes quite important. There's not enough work on that direction. I encourage you to think more about it.
Hi, I'm Lisa. Thank you for the great talk. And I have a question about what are your thoughts on deploying AI systems in the real world for collecting realistic feedback from users, perhaps even knowing that the systems are not perfect yet? How do you decide when it's safe enough? And this is sort of in a context because we have seen recent examples where systems were deployed or imperfect demos have been put out there and they have caused a big backlash, partially because capabilities may have been overpromised or the harms may not have been appropriately addressed.
Yeah, you're right. You're right. Well, there's a price to it, but I think we have to do it. At least companies that are deploying these systems need to do more effort to test it properly, to evaluate its weaknesses, its potential misuse before it's deployed. I mean, one problem is we don't have sufficient regulation regarding computing in general. I mean, AI in particular, but if you were to deploy a new chemical or a new vehicle, a new airplane, you would need to go through tons of paperwork to prove that your new thing is not going to be hurtful. But there's no such thing for software or hardware. So I think we're due for an upgrade of our regulatory system. Now that computers are everywhere and are having such an important influence on our society, it's a crucial necessity. The good news is that governments are starting to think about it. Yeah, but it's slow.
Hi, thank you so much for the talk. My name is Aziz Idris from Iowa State University. You mentioned in your talk that you've changed your minds a few times. I was wondering, what are factors that you consider or that makes you change your mind? And beyond some of the things you talked about as what you're working on for the future, what do you look at as the next thing to think about or to look at? Thank you.
Right. So the problem with changing your mind isn't about like what are the factors, what are the things that are interesting. Lots of things are interesting. The problem is the problem is letting go of things that you believed. We have, our brain tends to cling on things that we thought were true at one point. And we have to kind of really go against that. Like, put everything into question. Don't take anything for granted, even if it's written in a paper or in a book. Think by yourself. It's just reasoning. It's just like coherence. It's just going after truth. Follow your intuition. And sometimes your intuition says something different than when you thought before, and don't reject it. Yeah, and what's next? Every researcher has a different opinion. If you just check my recent talks online, you'll see what I think is next. I gave you a glimpse at the end of my talk.
Okay, I think there were like many more questions, but we need to keep 5 minutes to switch to the next speaker. So thank you so much, Yoshua, for giving your time, for opening this new in machine learning workshop. We're really grateful, and yeah, thank you so much.